Okay, so we mentioned that in quantum theory, quantum mechanics, once we constrain a particle, and ultimately this sort of means that we create a box, then we know that we get discreteness, and so we can count. And so let's think of the uncertainty principle, right? So in one dimension, delta x, delta p is more or less, let's just say h bar, right? It's h bar over 2 pi, but it's basically h bar. So we have some number, and let's take advantage of this to be able to count states, right? So in other words, if we have a particle in a one-dimensional system, so let's say some length x or x max, right? So that's the total length of the region where the box can live in this one-dimensional universe. Then delta x would be the uncertainty, so the range of possible positions associated with that state, meaning the particle is, we can say that's one possible state where the particle has this uncertainty, delta x. And so then we can sort of divide up that entire space by delta x and see how many of these states there are, right? So if we have a two-dimensional system, then that means we're dividing both sides, right? So we basically create a situation where this is delta x on each side, and we can now count the number of states associated with that uncertainty. So maybe the best way to count is to say that, right, so let's say 1D, this is a 1D multiplicity function. And so we would say the total distance, x max over delta x, that would be some pure number. But the particle is not, we're not just counting the possible positions in space, right? The particle also has ultimately an energy, but given the uncertainty principle, maybe we want to think of momentum. So how can we count the momentum states, the number of states associated with a certain momentum? Well, it's the same kind of thing, right? We would say there's some maximum momentum associated with some energy, right? So we have a P max squared over 2 times the mass, that's some energy, or some maximum energy. And we want to cast it in terms of momentum, and so we would do P max over delta P. That would be a number associated with the space of momentum in this one-dimensional system. And so we could then say, so first of all, to notice that this would be x, right? It would be this length times this value of momentum. I need to get a new pencil. Times that value of momentum, so we have P max, and delta x, delta p is this number, so that would be an h bar. And we can then think of making this three-dimensional, right? So the particle is not confined to a one-dimensional world, but a three-dimensional one. But that's simple to then extend this idea to a three-dimensional world, right? We make it a volume, so x max times x max times x max, right? That's a cube, and so we have a volume, and then P max cubed, and then we just divide that by h bar cubed, right? Because we're just multiplying this uncertainty relation, and so we have a cube there, and so that's a multiplicity function, right? We can think of this as a possible multiplicity function for one particle in a three-dimensional cube. What about a multiplicity function for n particles? What would that look like? Well, it would be this to the n. So we would have p max to the 3n over h bar to the 3n. And so that looks like there's a way of counting this system in this box, this universe, which is a box. We're assuming it's a box. And then we can go further by recognizing that the real world is quantum mechanical, and we have things like indistinguishability. But at least we are at a place where we start to see an actual value for the multiplicity function.